We welcome. So we welcome you, and we welcome you here today for our session. My name is Farah Jafar, and I will be your animator for today. So we will have this session under the name of what does the future look like for the oil and gas and energy sector. So it will be presented by our distinguished lecturer, Ian Phillips, in which we thank so much for being here with us today. So a brief presentation about this session. It considers the future of the oil and gas industry from two perspectives. The first half paints a picture of an industry in extremely good health and with an exciting future. Global population continues to grow and individuals' standards of living continues to rise. So the demand of the energy is growing steadily. Despite this growing demand, global proven reserves have risen as the technology improves. In addition, we know where there is a lot more oil and gas in the deposits that are currently uneconomic. But a small increase in the oil price would make these proven reserves in a nutshell. This industry might have a bright future. The second half presents the significant obstacle, summarizing the science of climate change and considering what happened when temperature rose this high in the past. The emerging alternatives, renewable energy efficiency, and some dramatic scientific advances in clean hydrocarbons will also be reviewed. The presentation closes with an assessment of the impact of these competing forces on the oil and gas industry, the developed world, and the human race. So, talking about our lecturer, Mr. Ian. Mr. Ian Phillips has over 13 years of experience in the upstream oil and gas industry with operators and service companies. In 2007, he became a founding director of CO2 Deep Store Limited, now Pale Blue Energy Limited, the first company specifically seeking to deliver CCS as a service. He holds an MSc in Petroleum Engineering from Heriot-Watt University and an MBA. He is also a fellow of the UK Energy Institute and is a chartered petroleum engineer. He recently completed 4 years as a chair of the SPE Aderbin section and was previously North Sea Regional Director of the SPEI board. He is an SPE distinguished member. So we welcome you here today, sir. And I guess I've talked about you briefly, but if you want, you can talk more.
No, that sounds like a pretty comprehensive introduction, and thank you. So good evening, everybody. As you've heard, my name is Ian Phillips, and I am one of the SPE's distinguished lecturers this year. Unfortunately, due to the small detail of the problem of COVID, a lot of my presentations will be delivered online. Although, as my partner pointed out, given that I'm talking about climate change, it's probably a good thing because the carbon footprint of visiting all of the sections would be quite high. Just so you're aware of it, I have got the chat box is open. So if there's any technical problems while I'm talking, please just pop a message in the chat. And at the end, I'd be very happy to answer any questions that you may have, and we'll use the chat box or invite you to switch your microphones on. So the presentation, as you've heard, is entitled, What does the future look like for the oil and gas and energy sectors? And we're talking about the energy transition. This slide is an acknowledgement of the financial support that the Distinguished Lecturer Programme receives, both from the SPE Foundation and through contribution from the profits that are made at the Offshore Europe Conference, which is held every couple of years in Aberdeen. So the outline of my presentation, as you just heard, it's kind of in 4 parts. I'm going to spend the first 5 or 10 minutes just looking at growing demand for energy. What's driving it? Why is it getting so big? and also how good has particularly the oil and gas industry been at meeting that demand. I'm then going to talk about the future supply, and as you've heard, there's a lot of it around, and we know where there's a lot more. So the first part kind of paints a picture of a very, very positive industry in a very rude good health and generally looking forward to a great future. But then there's this big but, which is that our product causes climate change. And I've got a couple of slides in which I will summarize some of the, I guess good representative academic papers that talk about climate change. And then the last third of my talking time will be looking to the future, and in particular, what place does oil and gas have in that future? So to start at the very beginning, this data is from the BP Statistical Review. So BP every year publishes a statistical review of world energy, makes it freely available on its website. The work is actually done by Heriot-Watt University's, what was called the Department of Petroleum Engineering, now called the Department of Renewable Energy. And what you see on the left is about 25 years of pretty constant growth in energy demand. The total figure, I mean, exajoules are a funny unit, but if I tell you that's roughly 200 million barrels of oil per day equivalent, obviously some of the energy is not from oil, but that gives you a rough idea of the scale on the right. And what you see is the colors show the contribution of each of the major energy types. So working from the bottom, green is oil, red is gas, gray is coal. So what you see is that hydrocarbons currently are providing around about 80 to 85% of global energy requirements. The balance, nuclear energy, hydro, and then the sliver at the top, the orange, is renewable energy. The two dips you see, one in around about 2009 when there was a global financial crisis and the world economy slowed down a bit. And energy demand has clearly been hit by the COVID virus and the dramatic cutback globally in travel, both air travel and all of these lockdowns causing people to simply stop driving cars as much as they used to. On the right-hand side of the screen, you see the relative share of the market. So what you see working from the top down is that the oil share of the market has been gradually declining. It's currently sitting just above 30%. Coal has been wandering along around 25 to 30%. Gas has been rising fairly steadily, currently sitting about 25%. And then there's a big drop right the way down. Hydro has been pretty constant. Nuclear has been declining slightly as some of the early nuclear power stations shut down. And what a lot of people see as the great hope for the energy transition, renewables, still a very low percentage, although you will see it growing very, very rapidly. Now, what sits behind this growth in energy is a growth in the population of the planet. So this data is taken from the United Nations World Population Prospect. So they publish every year, although the data is a couple of years out of date. This is the most recent one. And what you see is actual population to 2019. So in 2013, we were sitting at about 7 billion people. We must be well on the way to about 8 billion people on the planet just now. And the projections, well, they're just that, like any good petroleum engineer will tell you, just depends what assumptions you make. So the upper blue line assumes that the rate of people having children continues to as it currently is. So that is well above 2 children per couple globally. And if that happens, then by the end of this century, we'll be up around 15 or 16 billion people on the planet. So roughly twice what we have now. The lower blue line, in contrast, is a projection on the assumption that the global reproduction rate declines in a way that it has done in Northwest Europe, in North America, in Australia and in Japan, where the reproduction rate is about 1.3. So each couple is having less than 2 children, and as a result, the populations are beginning to contract. Now, that's not as silly as it might seem. For example, India has just reported that for the first time ever, its reproduction rate is below 2. So even when big population centers like that are beginning to contract, that projection is not as daft as it might look. But either way, by the time we get to 2050, we will be somewhere between 9 and 11 billion people on the planet, so significantly more than we currently have today. So all those people need energy. How much energy they want depends on their level of income. So at the very, very basic level, so people who are, for example, nomads in the desert in Sahara, or perhaps in the Kalahari Bushmen in Botswana, in southern Africa, they will be cooking and heating using biomass. So they'll be foraging for wood, and if they're really lucky, they might have candles for light, but mostly they go to sleep when it goes dark and they wake up when it goes light. Middle income countries have got a bit more. So they now have access to electricity. They have access to things like LPG in the form of bottled gas. Maybe in the towns they have gas supplied in by pipe. But they're heating and cooking with biomass, coal, kerosene. But now they're expecting lighting to happen a little more readily. So they've got kerosene lamps, maybe some electrical lamps. They've got refrigeration and basic appliances. And then there's what some of us take for granted. Certainly my part of the world, Northwest Europe, North America, some of the big cities around the world, electricity is available at the flick of a switch. Gas is piped to many, many buildings. Oil is available in the form of petrol or gasoline and diesel for transport. But what you see is that the energy usage has gone up. So when you multiply growing energy use with all of those people, you end up with an inexorable rise in the amount of energy that is expected. This forecast is a couple of years out of date, but it illustrates the picture. So Europe, United States, Japan, energy demand expected to contract as the population shrinks. But most other places in the world, South America, all of Africa, Middle East, India, China, Southeast Asia, all expecting the energy demand to rise significantly over the next 20 to 40 years. So pretty much a consistent picture with that growing population, growing energy usage. So what's been happening on the supply side? Again, from the BP Statistical Review, this graphic shows the remaining proven recoverable reserves of oil. It's 3 snapshots: on the left in the year 2000, in the middle on the year 2010, on the right in the year 2020. And one of the weird things is it's been going up. So even though we have been consuming nearly 100 million barrels of oil a day, the availability of recoverable reserves has actually been increasing. Now, this is partly due to improved technology, things like 4D seismic, horizontal wells, partly due to improved production technology, so fishbone wells, for example, understanding of water flood and gas flood, CO2, EOR, and so on. So generally, we are pretty good at finding and extracting more oil. It's also interesting to see where the geography is. So the orange area is the Middle East, absolutely dominates the world oil supply, nearly half of the world's oil sitting in that geographical area. The interesting one, bottom left on each of those circles, is the green, the dark green. That's South and Central America. And you see a big jump between 2000 and 2010. That's because in Brazil, they found some of the world's biggest oil fields offshore from Brazil, underneath the salt. They were able to image with seismic. They found big reserves. And you see the other areas relatively modest. The one that always hurts me is that the Europe, which mostly means the North Sea, so my backyard, as you can see, is down to 0.8 billion barrels rather of reserves, so very much on its last legs, the North Sea. The situation is very similar in gas. Same snapshots, 10 years apart, same increase in reserves. Slight difference now, the purple area is Russia. So Russia, very, very substantial gas reserves there. And as a result, Europe drawing a lot of its energy from there, but also a lot of gas in the Middle East, which we're seeing in the form of LNG being shipped around the world. In addition to those proven reserves, there's a lot of oil that we know where it is, and really it doesn't take much of an increase in the oil price to justify it. I often get asked about the ultra deep water places like Gulf of Mexico, offshore West Africa, offshore South America, offshore Northwest Europe. To be honest, not much. These are not likely to be very big reserves. By comparison, the big circle on oil was about 1,700 billion barrels. And similarly, high pressure, high temperature reservoirs, of which there are a small number around, likely to be a fairly modest contribution. But where it starts to get big is in the heavy oils and the tar sands. So tar sands, very, very big in Alberta in Canada, heavy oils, particularly in Venezuela. And we've got nearly twice our current proven reserves are estimated to be tied up in heavy oils and tar sands. Pretty messy to produce them, but it's a resource that we could tap into. Similarly, shale oil and shale gas, very, very preliminary estimates would suggest that we've got twice as much reserves as we currently know about, both in oil and in gas. So a total of 4 times the known reserves in that area. I mentioned biofuels for completeness. I think they'll be quite modest, mostly because they compete with agricultural land. And of course, the growing population needs feeding as well as needing energy. So biofuels, I suspect, will be quite modest. If we were to deploy carbon dioxide for enhanced oil recovery on a large scale, maybe another couple of thousand billion barrels. So again, global reserves all over again. And there's a lot of oil expected in some places we've still not drilled much. So a good example of this would be the Arctic. At the moment, it's banned for environmental reasons. But if we were to go drilling there, we'll probably find the same amount of reserves as we know about already. So an awful lot of hydrocarbons that we know where they are, and we could produce them if we were minded to do so. And finally, the best place to look for oil is always where you've already found it. Globally, the recovery factors are around about 35–36%. That means we are leaving well over 60% of oil in the ground. So technologies that can improve productivity from existing reservoirs are a good thing, are always a popular thing, and could probably add global reserves all over again. So far, you would say this should be an industry that's in a great place with growing demand and plentiful supplies of the product. Really, we should just be getting after it. But there is that very big but, and that is that our primary product is causing climate change. Now, I'm not planning to go through climate change in great detail, but I've got a couple of snapshots just to give you a sense of where the climate change science is. So this graph is a plot of the atmospheric CO2 content, and it's measured at the Mauna Loa Observatory. And its main feature is it's a long way from anywhere. It's on the top of a volcano in Hawaii. There is no big industry in Hawaii. So it's widely accepted by scientists worldwide that what is measured there is a good representation of the average CO2 content in the atmosphere globally. And what you see from 1960 is a pretty steady rise from below 320 parts per million to currently about 420 parts per million. So it's gone up roughly a third in that 60-year period. The black line is the rolling annual average, and that's just pretty much straight up. The red sawtooth is the monthly data. And what it shows is that in winter in the Northern Hemisphere, so where North America, Northwest Europe, some of the big population concentrations, also in Japan, are cold, then we burn an awful lot of gas to heat and the emissions go up. Then spring kicks in, it warms up and plant life grows a lot and it absorbs CO2 from the atmosphere. So the average figure goes down, but then it all repeats itself the following winter. And that's why we get that up and down on the red line. The other thing to observe is that it's pretty unambiguous that global temperatures are rising. What this shows is the horizontal line is the average for the last century, and the blue lines and the red lines are the deltas between the average and the actual temperature in that year. So what you see is that from 1880 to around about 1940, the temperature was consistently below average for the last century. And since about 1980, it has been consistently above average. In fact, 18 of the 19 warmest years on record have all occurred since the year 2001, and 5 of the warmest years on record have all occurred since 2014. So, pretty clear evidence that the average temperature on the planet is rising. The linkage between CO2 and temperature has been made in literally tens of thousands of peer-reviewed scientific papers. But for me, one of the most visually persuasive is this one. This is the Vostok Ice Core. It was cut in 2002, and the data was published in 2003. And what they did was they poured 2.2 miles, so about 3 kilometers, straight down into the Antarctic ice. It's called the Vostok Ice Core because the lake underneath, peculiar combination of temperature and pressure, means that this is liquid water, but it's well below 0 degrees C, but it's kept liquid because of the pressure. So it's referred to as the Vostok Ice Core. Near the surface, it looks like this. So you can see it's compacted snow. But the interesting thing is that brown sort of ring. That is the snow in Antarctica in the winter literally washes the atmosphere. It drops all of the microscopic flora and fauna out of the air and deposits it as a layer. As you go deeper, the compacted snow compacts further and it becomes ice. So what you have is little bubbles of air from the time that the snow fell, and these layers of organic material. So what scientists did was they measured the CO2 concentration from the little samples of air, and they inferred the temperature from the flora and fauna that was found at that particular age. And what you see is this zigzag line. So the temperature lags CO2 slightly, but pretty closely it tracks the CO2 concentration. So for me, one of the more persuasive pieces of evidence that there's a linkage between the CO2 concentration in the air and the temperature. If you take a slightly long view of temperature, this graphic is logarithmic scale from right to left, and it goes back about 500 million years. And what you see is the actual temperature, which we've inferred from core data and flora and fauna in the core data, and it's compared to the 1960 to 1990 average temperature. So what you see is that from about 5 million years ago to 500 million years ago, it was quite a lot warmer than it is today. And that was as the Earth was forming and then settling down. More recently, it's actually been cooler, and those zigzags in the last sort of 20,000 to about a million years ago is the ice ages that have come and gone, where the planet has been noticeably colder, we've had extensive ice, and then it's warmed up again. And then if you just look at the last 10,000 years, what you see is the temperature has really hovered around the average that it's been recently. But then you look at the far right-hand end, and that is the range of projections of what will happen if we don't do anything about climate change, suggesting that there could easily be a 4 to 6 degree average temperature increase on the planet compared to what's been normal for the last 10,000 years. So quite a worrying observation. And the projections of quite how warm we're going to get, of course, has been a matter of much speculation. The data on this slide comes from something called the IPCC. The IPCC stands for the Intergovernmental Panel on Climate Change, which is a United Nations body of scientists. They don't do any new science, they just review the science that others have done. And what you see on the left-hand half of the screen is a series of projections of the global surface temperature change. The red line is what you might call worst case projection. The blue line at the bottom is best case if we really get our act together. And if you look on the right-hand side of the screen, what you see is so the upper half relates to the red line on the left-hand graph. And what it's showing is that actually, although the average might only be 4 degrees, much of the land around the world will be in the order of 7 to 9 degrees warmer, degrees C this is. And the really worrying bit is that up near the North Pole, the temperature will probably be something like 11 degrees warmer than it currently is. Averaged across the world comes out at 4 or 5. And at the bottom is what happens if we really get our act together and the blue scenario plays out. Then we sit at around a degree and a half warming. It gets a bit warm near the North Pole, but nothing terribly worrying. Now, of course, these are projections. There's a lot of different scenarios which are in the IPCC reports, but I have to say they all look pretty much the same. Debate about exact number of degrees going up, but nobody's saying it's not going to happen. Some evidence that for me is quite alarming. This is the island of Greenland, just offshore from Canada. Using satellite data, they can measure the height of the ice. And what you see on the right is a map showing in red mass loss. So it's, in this case, it's millimeters lost relative to previous data. So you see the darkest red, they've lost 600 millimeters of height on the ice. And the blue is where the ice has got a little bit thicker because the top is now a bit higher. But you see a lot more red than you see blue. And the graph on the left is two different interpretations of the data on the right, but pretty consistent, suggesting that this century, the last 20 years, we've lost something like 4,000 billion tons of ice from Greenland. That is a sizable contribution to the rise in global sea level that we've already seen. And for me, probably one of the most worrying things in the papers that go with this is the calculation that if all the ice on Greenland melts, it'll add 7 meters to global sea level. So that means that, well, for instance, I looked up where your university is. It's going to get very wet. Countries like the Netherlands don't work. Big cities that are on the coast, like London, like New York, like Los Angeles, like Tokyo, like Guangzhou in China, all the way around the world, coastal cities suddenly cease to function because 7 meters of water is just enormous. The worrying thing is that most energy projections anticipate that hydrocarbons will continue to be burned pretty much unrestricted for decades to come. And if that happens, by 2050, we will be emitting around about 55 gigatons. A gigaton is 1 billion tons, so 1,000 million tons of CO2, up from the current figure of about 37 gigatons. And what you see on the different colors is this burning happens in many, many different places. So the residential one, for instance, that's the heating of homes, literally millions and millions and millions of homes worldwide, where we heat the homes when it gets cold. The power generation is the biggest one. That's the electricity we think we should have as a right to, we should take for granted. Huge consumer of hydrocarbon energy, and as a result, a big emitter. So quite a depressing picture. The thing that probably worries me most is there is evidence in the geological records that suggests that about 55 million years ago, there was something that everybody refers to as the PETM, the Paleocene Eocene thermal maximum. And what you see is that the ocean temperatures were something like 4 or 5 degrees warmer than they had been either side of this abnormality. There was the evidence from the geological record is that there was rapid alterations of marine and land-derived organic matter. There is evidence of storms lasting thousands of years. And probably the most worrying one is evidence that between 40 and 60% of all living things on Earth disappeared. They became extinct. Speaking as a living thing, speaking as an organism, kind of keen for that not to be repeated. And depending on which forecast you look at, we're heading for between 1.1 and 6.4 degrees average temperature rise. So probably even bigger disturbance than the PETM. So, as they say, Houston, we have a problem. So what can we do about it? The first thing to say is that globally, the political climate is changing and changing dramatically. young people, and forgive me as somebody who's heading towards retirement, that means people like you, are blaming people like me collectively, the baby boomers, the people who have had their working lives between about 1960 and about 2020. And this young lady, I'm sure many of you recognize, is Greta Thunberg, who has become almost an icon, an image of the anger that a lot of young people are feeling at the politicians, the older people on the planet, for not acting and for not doing something. In Northwest Europe, there is a very active pressure group called Extinction Rebellion. They have done a lot of very dramatic gestures, but they are making the point that we can't go on as we are doing. And it's begun to have an effect on politicians worldwide, regardless of how much of a democracy or a dictatorship exists. Major countries globally have now committed to net zero emissions by the middle of this century. The UK goal is by 2050. China, which has a bigger challenge, has now said by 2060. India announced at the COP26 conference in Glasgow, 2070. If you think about those dates, they are only 25 to 30 years from now. For us to achieve the scale of change by then, we're going to have to be on a pretty dramatic road of change happening much sooner. And of course, this is a global phenomenon. Right now, there's about 1 of the 8 billion people on the planet have done most of the damage and are continuing to do a lot of the damage. So Europe, North America, Japan, Australia, the big industrialized countries, they're the ones that have done much of the emitting over the last 50 or 60 years. And more recently, China and India have become major emitters. And in fact, in some cases in Northwest Europe, countries are very proud that their emissions are going down. But if we're really being honest about it, what's happened is we've outsourced a lot of manufacturing to India and China. So the emissions have moved location, but they're still happening. And of course, risk of stating the obvious, CO2 doesn't recognize international boundaries. This is a problem for the whole human race. It just happens that roughly 1 billion of the human race are causing much of the problem. The oil industry is beginning to respond. So any of you who attend SPE conferences will know that net zero is a big theme of many of these conferences. In the North Sea, the Norwegian and UK oil industry announced something called Vision 2035, which I'll describe in a moment, but it's a vision to decarbonize the industry. But if we're being brutally honest, those outside the industry don't really believe us. And I think quite a lot of people in the industry don't believe us either. And if you go outside of Northwest Europe, the global oil industry, I don't think is anything like as bought in as you would wish. So what is this Vision 2035? The first objective is to decarbonize the process of production. Oil and gas production is about 3% of UK emissions. So the oil industry is getting after that. Much more challenging is the process of decarbonizing our product. So converting oil and gas into hydrogen and burying the resulting CO2 using carbon capture and storage, or if we're lucky, utilizing the CO2 for other purposes. Decarbonizing the production process is actually not that difficult. It's quite an energy intensive process, whether you're onshore or offshore. There will generally be big electricity generation in the field, whether, as I say, on platforms or just out in the gathering stations in the field. Offshore, 80% of the emissions actually come from gas turbines. So there are major initiatives to decarbonize this. Equinor, the Norwegian state or part state oil company, is planning to build a floating wind farm near some of its major producing facilities in the North Sea. It won't completely decarbonize the production process, but there'll be enough power for probably 85% of the time. So they'll just put on the gas turbines when the wind isn't blowing. And wind brings me on to talk about how energy supply in general is changing. Wind is a massive energy resource, which is readily available in a lot of places, and in particular, readily available offshore. So what you see on the left is a big wind farm in Denmark. And on the right is an experimental wind farm, which is just visible offshore from Aberdeen. These are the biggest wind turbines in the world. Those individual blades are 100 meters long. So you can see these are absolutely enormous structures generating vast amounts of electricity. Of course, solar energy is widespread available, so particularly in your country. These pictures, the one on the left is from California, a big solar farm. The price of solar energy has come down so much that solar energy in California is now cheaper to produce than conventional gas-fired electricity generation. Picture on the right, I think, is in either Morocco or Tunisia. These are mirrors reflecting the sun's rays up to the top of the tower, where they boil water using the heat from the sun, and they make steam from which they generate electricity. So major attraction, but of course there's a big disadvantage. These don't work at night. So energy storage, I think, is going to become a major issue in the future. People are also looking at harvesting the energy from the movement of water around the planet in the oceans. The picture on the right is of effectively it's an underwater wind turbine, except now it's going to respond to tidal flows. And the attraction of tide is that it's consistent and it will work for probably 22 or 23 hours a day. Just as the tide turns, of course, it will stop working. Now, I mentioned storage, and there are some absolutely massive strides being made there. On the left is a picture of Elon Musk's gigafactory in Arizona in the US. And on the right is a picture of the power station that is powering a town of 30,000 people in Australia. The solar panels, which is the left part of the photograph, during the day generate enough electricity reliably to power the town and to charge up the boxes on the right, which is a big array of batteries. And the batteries provide enough power for the town for the nighttime. Now, realistically, that works at the scale of 30,000 people. It wouldn't work at a scale of a city of 10 million people, but it does illustrate what is becoming possible. More practically, we can store energy by pumping water up the mountain. So this is a place in Wales, part of the UK, and they pump water from the lake at the bottom to the top of the mountain when electricity is in oversupply. And then when they need the electricity, they let the water flow back down and they generate hydroelectricity. Another big future movement, I think, is to convert electricity produced from wind turbines into hydrogen. So the devices on the left are electrolyzers. You apply an electric current to fresh water and you get oxygen and hydrogen as a product. And you can store that hydrogen in things like salt caverns or in depleted gas fields, and then produce it back when you need it. There's also some interesting developments in small-scale batteries. So bottom left is a product from Tesla called a Powerwall. The Powerwall is installed at an individual house. It charges either from off-peak electricity from the grid or locally from solar panels on your own roof, and it supplies the electricity whenever you need it. And on the right, far right picture is thermal storage. So you use electricity to heat up oil, and you store the oil, and then you can use it to heat houses. So all sorts of concepts being looked at to store energy. And you need to store energy both within the day, because our demand for energy goes up and down during the day, but also between seasons. So when it's cold in winter, we need more energy. Some of this change is becoming visible. So Europe has decided that we will not be allowed to purchase gasoline or diesel-driven cars after 2030. As a result, all the big car manufacturers are developing electrically powered cars. Bottom right is a quite expensive one, courtesy of Tesla. Top left, much more affordable, the Volt from Chevrolet. And There are even talks about making trucks electric. So this is a Tesla designed electric unit to haul containers around on the roads. Rail transport is experimenting with compressed hydrogen as a fuel. All of these trains are operating with hydrogen. So the hydrogen is used in a fuel cell to produce electricity, which then drives the train. The hydrogen, of course, can come from wind, or it could come from converting oil and gas into hydrogen. Even aeroplanes are changing. This picture is of an experimental craft called Solar Impulse 2. It flew all the way around the world on electricity, and the top of the wings is a series of solar cells. Now, to be fair, it took them 7 months and it had 1 passenger, so it's not a practical solution to air travel. But this is an electric aeroplane being developed by Airbus, one of the big airline manufacturers in the world. This is the world's first flight of a hydrogen-fueled aeroplane. And the current estimation is that hydrogen could probably fuel short flights up to perhaps 500 or 600 kilometers quite easily. Some of the bigger, more forward-looking companies are looking at some quite dramatic changes. So the picture on the left is a computer-generated image of a helium balloon, an airship, covered in solar panels, so it can capture electricity, stores the electricity, uses it to drive the engines, and also to drive compressors, which, if you want to go up, you release helium from pressurized containers. When you want to go down, you suck the helium back in and you store it. And the big attraction is that the big blue bit underneath is what you would travel in. So although this would travel about half the speed of a regular jet plane, but much more comfortable to travel. So quite a realistic way of doing long distance travel and making it zero carbon. On the right is the picture that represents some of the experimentation that's going on to decarbonize shipping. Ships tend to burn all the rubbish from the bottom of an oil barrel. They call it heavy fuel oil. Massive emissions come from it. It's as bad as coal. So companies are looking at doing carbon capture and storage on ships, as you can see here, using very cleverly engineered sails to at least augment the power on the ships, and a range of other solutions trying to decarbonize shipping. This graphic, also from the BP Statistical Review, shows the growth in renewables. Remember, that's still less than 5% of total global energy, but what you see looks to me remarkably like exponential growth. There is huge money being poured into renewable energy. And as you can see on the graph on the right, the yellow is the massive growth in solar, blue is the massive growth in wind. So realistically, we could power our planet with renewable energy quite readily. One of the more depressing figures is to be shown on here. So we're currently emitting about 37 gigatons of CO2. There is a not-for-profit company based in the UK called Carbon Brief, and what they have done is brought together all of the science and told us how quickly do we need to act. So if we're willing to live with a 1.5 degrees C rise in global temperature, we need to move in the next 4 to 15 years. And the 4 to 15 years reflects the uncertainty in all of the models. But even the most sort of cautious, optimistic models are thinking sometime in the next 15 years it's going to be above that. Some of the more aggressive models suggesting it might happen in the next 5 years. And as you can see, 2 degrees C is between 19 and 31 years. 3 degrees C will hit it between 54 and 75 years. So some quite big cutbacks in our emissions are going to be required. And to put that into context, all of our known reserves of oil and gas, if they're consumed, they will produce about 2,800 gigatons of CO2. To avoid emitting that, either we have to leave 80% of that in the ground, which of course would be unworkable for the many countries like yours that are very dependent upon hydrocarbon production, or we need to find a way to avoid these emissions, and quickly. So decarbonizing oil and gas, well, actually, we know how to do it. We can split down hydrocarbon molecules. We produce hydrogen, which is the fuel that you would use, and then we produce lots of carbon, either as black carbon powder or as carbon dioxide. But we'll have to dispose of that somewhere, possibly in the reservoir by injecting it, as we do in CCS. Maybe we have to bury it. Maybe we can turn it into useful building blocks. So as I say, the technology exists. Steam methane reformation and the recent adaptations of that can break down hydrocarbons into hydrogen. There is some process engineering using carbon as a catalyst, which looks like it would work to cause hydrocarbons to break down. And there are some biotechnology. There are patents on genetically engineered bugs, which could break down long chain molecules and produce hydrogen. So we're getting to the end now, but my view of the future is it's pretty complicated. A very complex technological and political balancing act is going on right now. I'm real clear, we are ruining our planet by burning hydrocarbon in pretty much every aspect of our civilization. And if we don't do something about it, the planet that we call home is going to change dramatically. So we're going to have to do some big changes. Low carbon alternatives to just conventional burning of hydrocarbons and making hydrocarbons low carbon. One of the big challenges is the public, by which I mean the mass public, not engineers and scientists. They understand about this climate change thing. They've heard about it. It's in the papers. But they kind of would like life to go on as they do at the moment. So being able to travel, fly away to exotic locations for nice holidays, they still want to be able to do that. So things are going to change. Air travel, not sure we'll be doing as much of that, but if we do, we'll find ways to offset it. Road travel, particularly trucking, will almost certainly switch to hydrogen, which is more lighter weight and more compact than batteries in the vehicles. Maybe we'll have to stop shipping quite so much stuff around the world. It's quite remarkable how much food gets flown around. We don't really need to ship quite so much around. Maybe we need to get smarter about our supply chains. Some of you will recognize the iPhone. There are components in there from 30 different countries. So the components obviously have to travel with a big carbon footprint. And of course, I think our energy system is going to change dramatically, heading towards renewables. So I'm thinking that the solution is going to be a mix of things. We're going to have to decarbonize electricity production with wind, with wave, with solar, burning hydrogen, and figuring a way to store energy. We're going to have to decarbonize heat with electricity, producing hydrogen, energy storage, and an implication is that natural gas will be phased out, I suspect, because we turn it into hydrogen. We're clearly going to have to decarbonize transport because there are literally billions of small CO2 emitters driving around the planet. We call them cars and trucks. And maybe we'll have to figure out how to use less energy. Where I live in Northwest Europe and in North America, buildings are extremely poorly insulated. We actually do a lot of heating of the air around the building because the heat leaks out through the walls. So doing insulation is a very simple way of achieving energy efficiency. And I think realistically, we're likely to see some quite big changes in our lifestyles. So, ladies and gentlemen, I hope you found that interesting. I also hope as petroleum engineers that you don't find it too depressing. I do get asked quite a lot, you know, I'm studying petroleum engineering, should I change to something different? I think the truth of the matter is we're still going to need oil and gas for many years to come. What we're going to have to do is figure out how to decarbonize it. And that means that you'll probably have to learn new skills. Injecting CO2 into reservoirs, well, that's just a different fluid from what we already do. We already inject natural gas and water and produce oil and gas from reservoirs. So it's just a different fluid. Maybe storing hydrogen is going to be another big requirement. So I think we'll need a lot of petroleum engineering skills for some time to come. So I'm not sure, how do you want to handle the Q&A session? I'm happy for people to put questions in the chat. I've already seen one, which I'll speak to in a minute. Or I'd be very happy if you wanted to raise your hand, and which I think you can do with on your screens, and then perhaps put your microphone on and speak. So can I ask for my hosts, are you okay if I just go ahead and read the questions and do the answers?
Yes, you can go ahead. I think the participants are welcome to put their questions in the discussion box.
Yep.
So I guess we will read the question from it and then answer them.
Okay, so the first question says, do you think that natural gas could play an important role in the energy transition? Coal power plants are moving to natural gas in many regions of the world. Maybe the current crisis will push investors to move to natural gas instead of renewables. So natural gas has been very, very cleverly presented by the oil industry as a transition fuel. Compared to coal, it emits about 60% of the amount of CO2 per megawatt hour of electricity generated. So it is better than coal for sure. And where you've got a lot of natural gas, it is logical to build a natural gas-fired power station rather than a coal-fired one. But to achieve net zero, we have to decarbonize the natural gas as well. Natural gas is actually a lot easier to decarbonize because when it burns, it's a lot cleaner. So the carbon capture and storage technologies work a lot better. But my view is we have to be thinking about decarbonizing the natural gas and using the natural gas to replace coal. So if you like, both. Next question was any analysis done before the decision to achieve climate neutrality by 2035? Is there any analysis available studying the effects on the whole economy of a CGE model? So I think when you look at climate change and energy transition, you have to take off your conventional economic hat. We are trashing the planet we live on. This is about the survival of the human race. I don't think I'm being too dramatic when I say that. So yes, it's going to cost more, but historically, for the last 50 or 60 years, we have simply dumped our CO2 into the atmosphere for free. So that's what's changing. In Europe now and in North America, there are emissions trading schemes which are putting a price on CO2 emissions and driving a simple economic logic which says, let's clean things up. So I think yes, there have been many studies of the whole economy effect, but interestingly, although the energy cost goes up, it goes up for everybody. So if you like, the spend profiles change, but what it does is it creates a whole new load of opportunities for industry. So actually, many jobs are created and a lot of value is created by generating this new industry. And we're doing it because we're doing something about the planet. A question, thank you very much for the comment about the presentation. I'm glad you enjoyed it. Where can you obtain the webinar? So this one is being recorded. So my expectation would be that your student chapter will post it.
About this one, the webinar will be shared on our YouTube channel afterwards.
Okay, there we go. And then the next question says, do you think that climate initiatives will be placed on the back burner because of COVID-19? And what about the latest COP26 proposals? Can we still rely on this event, since I believe that even the ones who are proposing solutions are not applying them in reality? Yep, the oil and gas industry fuels the economy of the country. Do you think these countries are ready to reduce production of fossil fuels and put their economy at risk? So what you've identified is absolutely the challenge facing the human race. What I see is that the governments of the industrialized world, if you like, the ones who have benefited from the historic emissions and who have done a lot of the emitting, are doing a lot of the heavy lifting to start the process of decarbonisation. So the UK government, for example, is making subsidy arrangements available to support industry to decarbonise. The US government is planning to do the same, as is the Japanese government, and even the Australian government, which has been dragging its feet, is beginning to make that sort of support available. So I do think that governments are moving. I also don't think they're moving quickly enough. The challenge for the countries that do depend on hydrocarbon production, obviously you live in one of them, and a big part of your national economy is powered or is funded because the oil and gas industry is there. And that's true across much of North Africa, much of the Middle East. There's a lot of countries in sub-Saharan Africa that are delighted that they've now got an oil industry. So these countries are absolutely hungry to benefit from the benefits that they can get from large volumes of oil and gas production. I guess the only point I'd make is you live on the same planet that I do. So we've all got to do something. So I could imagine a situation in which oil and gas fields of the future produce hydrogen. You process the oil and gas, produce hydrogen, and hydrogen is what is shipped to the market, the energy hungry markets of the world. Decarbonizing along the way, affordable because the countries that are consuming the energy have committed to decarbonize. It's just a very different form of the energy storage and energy transmission. So instead of big oil tankers and big LNG tankers trucking around the world, I think we'll have big hydrogen tankers, or more likely actually hydrogen stored in some other form, either in a metal or as ammonia. So I think it'll be a very different industry in the future, but I absolutely recognize the challenge that you identify. Who am I, or who's anybody in the developed world to say, no, just got to leave all that oil in the ground. It's not going to happen, but we do have to do something about the emissions. And then another last comment at the moment, question: what is the narrative to support 100% renewable energy systems modeling, especially in the hard to electrify and decarbonize sectors like heavy industry? So I think that I think a couple of things to understand. One is that hydrogen is a viable energy delivery mechanism. So many of the processes that currently rely on burning oil or natural gas can be decarbonized by using hydrogen. So that works so long as the hydrogen is produced in a low carbon way, possibly from renewable electricity or possibly from oil and gas. So the renewable energy system is, if you like, it's renewable when you generate it, but I made the point about storage. So something has to happen because electricity doesn't store very well. Battery technology is improving dramatically, but yeah, I think hydrogen is going to be the intermediary for a lot of our future energy systems. It's also worth saying that the heavy industries are really seriously looking at what can they do to decarbonize. There is a pilot steel plant in Austria, which is entirely hydrogen driven. They have wind turbines, they generate electricity, they manufacture hydrogen, and they use hydrogen in the steel manufacture. Similarly, cement works can use hydrogen in the calciners. Interestingly, cement also produces CO2 as a big product of the manufacturing process. So carbon storage will be necessary for things like that. But pretty much every industry that is a big consumer of natural gas or hydrocarbons for fuel right now is researching using hydrogen instead. So I think the energy system in the future will be very, very different. Yeah. So I think we've come to the end of the questions. Oh, here we go. Another one. So we know that climate change is such a big challenge, but if we can't stop, can we slow it down? How much renewable energy do we need for that? The percentage that we need right now to gain some time searching for solutions. So the global energy demand was what was on my first slide. So measured in a rather confusing unit of exajoules. But roughly speaking, it's something like 200 million barrels of oil equivalent per day. So big amount of energy. Renewables, I think, will serve the purpose. I could imagine 30 or 40 years from now, renewables delivering most of, if not all of our energy. It really is, it could be that dramatic a change. And the oil industry might just be producing raw material for fertilizer and for plastics. But what people talk about, the energy transition. So between now and 2050, 2060, that's when we will be learning how to decarbonize hydrocarbons. And maybe that makes hydrocarbons work for much longer. Of course, hydrocarbons are hugely attractive. We know where there's a lot of energy in hydrocarbons. So as long as we can figure out how to sort the CO2 emissions problem, we'll be in good shape. So yeah, renewables, I think, certainly there have been estimates made of the amount of energy that hits the planet every day from the sun, so we can convert it to solar energy, and also about the amount of energy available if we were to capture wind. And in both cases, the total global energy requirement is substantially less than those figures. So the energy is available in a clean form. It's down to us to figure out how to make that work. And yes, I see a comment has been put in: BP, Equinor, Total are transitioning. Do the other companies have to follow? So my view is, if they don't follow, they will be history. I think it really is, it needs the big industrial companies. So, I mean, you mentioned BP, Equinor, Total. Saudi Aramco is doing the same thing. It's working on how can it decarbonize both its production process and its product. So, as I said earlier, I could imagine that you as petroleum engineers in the future will be doing things like managing the carbon dioxide that's produced from the hydrogen plant that sits at your gathering station. So you're producing and selling hydrogen as a product, and the CO2 disposal is part of the cleanup the problem. I think that's what transition looks like. And I honestly think the answer is every oil company in the world will have to follow it. This is a truly global scale challenge. So we're up at about an hour of talking. Very happy to answer any other questions, but also very happy to wrap up if that's appropriate.
We thank you so much, sir, for your information and your presentation. It was really a fruitful one, and one of the best lectures we had in this year.
That's very kind of you to say so. Thank you.
Thank you. And we thank the participants for being here with us today. For any more information, you can contact us, or you can find the lecture which will be published on our YouTube channel, Petroleum Club SPE University of Boumerdès Student Chapter. So thank you, everyone.
Okay, thanks. I also noticed you've got a President's Award on your logo, so congratulations on that.
We thank you so much. It's such a great event, and we are proud of it.
I'm sure you are. So Aberdeen section won the Best Section Award when I was chair, and I was very, very proud of that. So I'm delighted to meet you all. I wish you a very happy evening, and hopefully this COVID virus will mean that we can actually do some traveling in the not too distant future. So thank you and good night.
Thank you, sir. Good night to you as well.